In the previous session, we have looked at algebra of matrices with respect to equality of matrices, addition, subtraction, scalar multiplication, and transpose of a matrix. Now we will look at multiplication of matrices. Given two matrices, A of order M1 by N1 and B of order M2 by N2. We can multiply the matrix A by B only if the number of columns in A is equal to the number of rows in B. That is, A sub M1 by N1 times B sub M2 by N2 is defined only if N1 is equal to M2. The number of columns here is equal to the number of rows here. Briefly, let's go back to our first session. That is the introductory session. There we had seen this system of equations. 4x plus 3y equal to 5, x plus 6y equal to 2. And we have seen that this can be written as a matrix equation, where we have a coefficient matrix times the variable matrix equal to the constant matrix. So 4x plus 3y is equal to 5. 1 times x plus 6 times y is equal to 2. So that is how we had described this system of linear equations in matrix form. But what if we have two systems of equations with the same coefficient matrix but different constants, constant matrix? No point in writing them separately. We can combine them into a single matrix equation. How would we do that? So if you notice, x and y forms a single system of equation, these two combined. If we have two systems, system 1 is 4x1 plus 3y1 is equal to 5. x1 plus 6y1 is equal to 2. That is our system 1, what was already there. Now let's say we have another system of equations. We have 4x2 plus 3y2 equal to 4. x2 plus 6y2 is equal to 1. So here you will notice that in system 1 and system 2, the coefficients are same, but the constants are different. Naturally, the x and y values will be different. So that is why we have made it as x1, y1, x2, y2. Now, how do we put it in the matrix form? We write it as another column in the variable matrix. So we have 4, 3, 1, 6, the coefficient matrix as it is, times, now we have two columns because we have two systems. So x1, y1, x2, y2 is equal to, and here again we have 5, 2 for the first equation and 4, 1 for the second system of equations. So again, if we have to revert back to this system of equations, how would we do that? We would take 4 times x1 plus 3 times y1 is equal to 5. Then 1 times x1 plus 6 times y1 is equal to 2. That would give us the system 1. For system 2, we multiply this matrix, rather the rows, with the second column. So 4x2 plus 3y2 is equal to 4. 1x2 plus 6y2 is equal to 1. So here, the variables of each system are placed in separate columns of the second matrix. Thus, each column corresponds to one system of linear equations. Each entry of the product matrix is obtained by multiplying the entries of a row of the first matrix with the corresponding entries of a column of the second matrix and adding the results. Hence, matrix multiplication provides a compact way to represent and compute multiple systems of linear equations simultaneously. Here, remember, for this to work, both these systems of linear equations should have the same coefficient matrix, or rather, they should have the same coefficients of the variables. We can look at it in another way. A matrix of order m by n operates on each column of a matrix of order n by p, producing a matrix of order m by p. Each column is transformed independently and corresponds to one system of linear equations. Let's say we have two matrices of order 2 by 2, A and B. Now we have to find the product of A and B, which let's say is going to be the matrix C. So the first element, that is C sub 1 1, will be equal to A11 times B11 plus A sub 12 times B sub 21. C sub 12 will be A sub 11 times B sub 12 plus A sub 12 times B sub 2. C sub 21 will be equal to A sub 21 times B sub 11 plus A sub 22 times B sub 21. And finally, C sub 22 will be equal to A sub 21 times B sub 12 plus A sub 22 times B sub 22. So our matrix C will be this. So here each element in C is a sum of the products of row elements of A with the corresponding column elements of B. Now let's look at product of 3 by 3 matrices. So again, we follow the same pattern of taking the sum of the products of row elements with the column elements, corresponding column elements. So this would work out to be like this. A11 times B11 plus A sub 12 plus B sub 21 plus A sub 13 times B sub 31. So first row, first column. Then first row, second column. Then first row, third column. That gives us the first row of the resulting matrix. Then we start off with the second row, first column. Second row, second column. Second row, third column here. And then finally, third row, first column, third row, second column, third row, fourth column to get this resulting matrix. Now, what that means, now that we know how to multiply two matrices, we can take powers of a matrix. So let's go back to our A equal to A11, A12, A21, A22. Our square will be A times A, which is A square, which will be equal to this. And this we know how to multiply. So A11 times A11, that is A11 square, plus A12 times A21. So first row, first column, first row, second column, second row, first column, second row, second column. To get this matrix, which is the square of a matrix A. Briefly summarize. Observe that each element of the product is obtained by multiplying the elements of a row of A with the corresponding elements of a column of B and adding the results. This requires that the elements match 1 to 1, and hence the number of columns in A must be equal to the number of rows in B. So if we have a matrix of order 2 by 3 and another matrix of order 2 by 3, then the product is undefined. Why? Because here we have 3 columns and here we have 2 rows. So this product is undefined. Whereas if we have a matrix P of order 3 by 2 and Q of order 2 by 3, then it is defined. And the result is a 3 by 3 matrix. Now, notice that the product here, P times Q, if we look at the product of, if we write the orders as a product side by side, then you will notice that the adjacent numbers must match. That is 2 and 2. And the outer numbers give the order of the result. Now, in short, this taking the sum of the products of the elements of a row in one matrix and the column elements of another matrix can be written as A times B equal to C, where Cij is equal to the summation as k goes from 1 to n of Aik, that is a particular element in A, times P sub kj. So here you will notice that we are taking the column element for a fixed I and j. Try to work this out and make sure that you understand how this works out. Okay. Now, multiplication of matrices have these properties. In general, A times B is not equal to B times A. That is, matrix multiplication is not commutative. A times B times C is equal to A times B times C. That is, matrix multiplication is associative. A times I is equal to I times A is equal to A, where I is the identity matrix of appropriate order. Now, the transpose of A times B is equal to transpose of B times transpose of A. This is called the reversal law, because remember, multiplication is not commutative. So here, if we want to take the transpose of a product, we have to take the transpose of each and reverse the order in which we multiply. Then we have distributive laws. A times B plus C is equal to A times B plus A times C, and A plus B times C is equal to A times C plus B times C. Now, A times B is equal to A times C does not imply B is equal to C. What does that mean? It means that we can't cancel A and A on both sides of the equation to get B is equal to C. Okay. Now, it is possible that A is not equal to a zero matrix, B is not equal to a zero matrix, but the product of A and B is equal to a zero matrix. That was algebra of matrices. That's it for now.